The following presentation covers verification, validation, and testing modules 5.1 through 5.3. This presentation is comprised from Group 2, including Paul Adame, Gary Adams, David Estrada, Luis Ochoa, and Jorge Zaversa. During this presentation, we'll give a brief introduction on testing standards and procedures. We're going to talk about white box testing, which includes component and code coverage and interface testing. We're also going to talk about black box testing and its basic divisions, which would be boundary value, decision table, finite state machine, and human system interface testing, or HIS.
The objective of the introduction is to define and explain what testing is and how to perform this process. This chapter explains the verification, validation, and testing definition of testing as a subset of verification and validation by actively operating and using the system and by verifying or validating it. During every system testing, the following must be confirmed, which are that the system is, firstly, doing what it should be doing, which is to conform to requirements, and that it does not do what it should not be doing. When it comes to the process of fundamentally testing a system, one should always include a list of system requirements and other important elements. Some of these other elements include the system specifications provide the measurements by which to judge the system. These also guide how to generate test cases needed to verify and validate the system. Test engineers, or a group of test engineers, perform the specification-driven test process. They solely determine whether the system succeeds in meeting all its specifications. The system specifications also form the foundation for the design and development for what the target system must do. This is what the customer will pay for after all. Figure 5.1 below illustrates the fundamental system testing process. The system specifications guide in creating the test cases, which in turn guide the tester on how to perform each test, which in turn he or she will mark as pass or failed. Those that fail or are unclear will go back and be analyzed or rewritten when the system is under test. The specifications will in turn go through the same process all over again, or if it must be retested, it will get retested by the tester and again given a status of pass or fail. White box testing. White box testing is undertaken with an internal or structural view. Therefore, it is referred to as structural testing. White box testing requires an implicit knowledge of the system's inner workings. White box testing also generally is done by using special features of the development environment, and this is performed on individual subsystems or modules partitioned based on the system's internal structure. White box testing demands that the test engineer select test case inputs that will exercise all paths and determine the appropriate outputs. The testing strategy deals with internal logic, structure of the unit under test, and it seeks to incorporate coverage of each element of the unit being tested. One of the advantages that white box testing has is that it can be derived from the intimate knowledge that the VVT engineer has with respect to the internal structure of the system under test, or the SUT. Another advantage is that it is easy to generate input data for testing the application effectively. Hence, attacking potential weak design points is very simple to perform. Another advantage is that it can add the benefit to encourage test engineers to carefully consider which implementation of the process he or she will take. And another advantage is that many of the tools that is used in this testing process already exist, depending on the test coverage or the complexity of the code. One of the major disadvantages of white box testing is that it stems from the fact that the VVT engineer must have the skills in the subject matter domains such as hardware and software. The VVT engineer must have an intimate and specific knowledge about the internal structure of the system under test. Another disadvantage is that the limitations to perform the tests can be exhaustive. Fully covering all aspects of the component structure is extremely difficult, depending on the complexity. And yet another disadvantage is the detection of missing or incorrect functionalities in the system under test occurs often.
Component and code coverage testing. This testing process places an emphasis on units composed of individual tests, ensuring that the lowest packaging level is functioning properly. This also helps to verify test sequences that are constantly used by the hardware components or software code and ensuring their functionality. This helps to build test suites to ensure units, devices, and lines of code meet the standards set forth by the organization. The methodology of this process would be to find test patterns from inputs that expose existing faults within the system by analyzing outputs. This detects lower level problems that will cost more when found at higher levels of packaging or production. Controllability over individual subunits within the system and observability of the outputs of subunits is also used in this process. In this slide, we cover component coverage testing and hardware. Potential hardware defects are complex and too numerous to simplify in modern technology. Factors to consider when testing high-level components are variability, non-permanent hardware faults that affect the unit intermittently, multiplicity, multiple hardware faults that affect hardware in unexpected ways, and effects on function and operating speed, which are hardware faults that manifest themselves over time or through a sequence of inputs. Generated hardware test patterns are as followed. Manual generation, which consists of a simulated model to verify fault detection. Pseudo-random generation, which uses test patterns that are randomly generated to explore outputs. D-algorithm, which are optimal solutions composed in a sequential manner. And path-oriented decision making, which is an improved version of D-algorithm that grows with complexity. In this slide, we cover component coverage testing and software. Test cases are built into software and are proved upon to ensure vital functions occur within the program. Typically, these test cases use three inputs, X, Y, Z. Examples of software component coverage are as follows. There's statement coverage, which verifies that one or more test patterns cause the execution of each and every software code statement at least once. In this example, 200 would hit every statement within the pictured function. Branch coverage verifies one or more test patterns will cause execution of every branch. In the example, 200 hits every yes within the function. Inversely, 000 hits every no within the function. Condition coverage will verify that compound conditions are executed at least once. In the example 310 will verify statements such as x greater than 1 and y equal to 0, as well as x equal to 2 or z greater than 0.
Interface testing. The objective of the interface testing is to validate proper interaction between systems or components. We evaluate the proper data and control flow between systems or components. Interfaces are also called contracts between systems or components. We'll be talking about 4 types of interfaces. The first type is hardware to hardware interface. For example, the electrical wires between a controller in one unit to a relay in another unit. The second one would be hardware to software. For example, a USB flash drive holding information to be read by a computer. The third one would be software to software interface. For example, a database transferring data to a HTML document. The fourth one would be human to system interface. For example, a graphical user interface. In this slide, we have an example of a system using interfaces. In this case, we have a black box serving a website. The black box, it's also consuming services from a third-party application, and it's also retrieving data from a database. Each of those links between the black box and the subsystems, it's called an interface, which's gotta be tested at all times. Method for testing an interface. First, we generate a fake element representing the future endpoint or the future interface we're gonna be interacting with. Second, we integrate and test the two interfaces together. We're gonna be looking for contract breaches. For example, an element expecting an integer and the interface returning a string. Interface and erroneous assumptions. For example, an element calling an interface that has no memory to work on, resulting in an exception, therefore failing with the response. Interface timing errors. For example, race conditions.
A type of black box basic testing is boundary value testing. This method verifies the behavior of systems at operating boundary areas by selecting test data values that lie at operating extremes. Boundary test values may include maximum or minimum values within the normal operating domain. Values just inside and just outside operating domain boundaries typically encountered operating values or specific error condition operating values. The objective of this method is to test systems at boundaries of the operating domain where a substantial number of errors tend to concentrate. Generally, this method is applicable to software, to embedded systems, and systems that contain some software components. The boundary value testing method is based on selecting test cases within sets of equivalence classes at the edge of the class rather than selecting any element at random. This method entails two-step operation. 1. Defining equivalence partitioning, and 2. Generating and executing test cases at extreme ends of equivalent classes. Step 1 is identifying equivalent classes. This step entails dividing the input domain into equivalent classes of data. Under equivalence partitioning, we define a test case that uncovers classes of errors, thereby reducing the number of test cases required. In other words, an equivalence class represents a set of valid or invalid states for input conditions. Step 2 is boundary value testing. This is applying boundary value testing. Requires a selection of test cases at each side of the boundary between equivalent classes. So for a valid range of values bounded by a minimum alpha and a maximum bravo, the test cases values should be alpha minus 1 at alpha and bravo at bravo plus 1. A boundary value testing method facilitates a possible reduction in the number of test cases relative to the number of detected errors. And although the system is not fully validated, a high proportion of errors could be found. However, the weakness of boundary value testing is that the testing process is not exhaustive, and the method is not appropriate for complete validation of the system. Decision table testing is another form of black box basic testing. It focuses on validating responses of a system under specified conditions and constraints. System testing is accomplished by means of a decision table, and it models complicated logical behavior in a precise and compact way. Construction of a decision table is accomplished in 2 steps. Step 1, identifying all the possible conditions and their combinations that could affect the behavior of a system. And step 2, for each and every condition identified in the first step, define all the possible system actions in response to these conditions and their combinations. Decision tables are typically structured into 4 quadrants. They are conditions, actions, condition alternatives, and action entries. The way to read it is, each condition corresponds to variables, whose values are listed in condition alternatives. Each action is an operation performed by the system under the stated conditions.
Finite state machine testing. This testing process evaluates systems for proper execution of control functions. It utilizes automated theory involving system states, events, transitions, and activities. The state of a system represents a stage in its life cycle when it performs activities or waits for events to continue on. The methodology behind this is to identify system states. The system will remain in a specified state until conditions are fulfilled. Specified outputs determine whether the state can change, and a system may fail a test if it is exposed to an internal or external event that it does not recognize. Strategies for FSM testing include state machine coverage. This is testing based on state event combinations, transition structures, and state machine paths. Testing strategies should include coverage for the following criteria: transitioning through all states, at least at a minimum, transitioning through all state event combinations, which can help detect more problems than what's covered, or transitioning through all possible one-time transitions, which can uncover errors from undefined FSM components. Typical FSM testing can adhere to some of the following activities: action fault, which is verifying activities on a transition that can be incorrect or missing. Guard condition fault. This is ensuring that guard conditions on transitions are correct. Missing transitions, verifying that transitions exist for legal events through states. A legal event failure, looking for unexpected events that cause failures. Unintended event failure, events that are unexpected causing complete system failure. State fault, checking for extra states in the system. Next state fault, transitions into illegal or incorrect states. And extra transition, checking for legal events that occur at unexpected states. The following slide is an example of FSM testing. The diagram displays a vehicle autonomous driver assistance system. In the diagram, all transitions are mapped out and connected to each other. The first transition would be power off mode, the initial state of the system, where the vehicle is non-operational. Next, it will go into the initialization mode. Here, the VAD performs all initialization processes. Next would be the operational mode, a mode comprised of 3 sub-modes, which include main mode, sensor monitor and traffic solution mode, and bit mode. Main mode is then decomposed into supervisor mode. In this mode, the VAD provides visual and audio warning to the driver. Autonomous mode. In this mode, the VAD is fully controlling all car performance actions such as braking and steering. And then finally, termination mode, the final mode that performs termination of all procedures.
Human System Interface Testing, HSI, is another form of black box basic testing. This method's purpose is to validate that the HSI is functioning properly from both the ergonomic and the functional point of view. HSI testing should consider both the input as well as the output boundaries between people, operators, and users of systems and the system itself. HSI deals with the boundary area between humans and engineered systems. More specifically, it deals with input devices, which are the means by which humans control systems, and output devices, which are means by which humans interpret system information. HSI performance determines how easily a user may control and comprehend underlying functions of a given system, and it is often the part of the system that determines the acceptability of the system by end users. Humans control systems by issuing appropriate commands. The outputs of these systems, stemming from these commands, are then monitored. Commands may take many forms. So when one considers this testing task of HSI, you should be aware of the range of devices used for interfacing with systems. The table below breaks them out by input devices, output devices, and combined input and output devices. Test engineers must take into account that each and every interface device connected to the system introduces a certain problem distinctive to the given device. A subset of human system interface testing is human input testing. To test a human input interface, in other words, a human controlling a system, one must first validate that the system responds correctly to proper commands or sequences thereof. Next, one must verify that the system recognizes, tolerates, and properly handles operator errors. Finally, we combine these actions into the requirement that the system is able to properly process both expected and unexpected input values. In a similar fashion, validating HSI outputs, called human output testing, where humans are monitoring a system, we generate and execute test sequences intended first to verify that the system meets its specifications and that humans react properly to the output information.